A few words about myself. My name is Stefan Kraus. I'm product manager for functional safety at HMS Networks. HMS, maybe some of you know, we are famous for communication, industrial communication. And my part is doing the safety communication inside HMS. In that purpose, I'm staying here today on stage, presenting you about mobile machineries from logic to action, simplifying the safety integration into mobile machines. And thanks, Dave, for the introduction, why we are here. I think the main topic that brings us together here is the regulations and safety requirements. Otherwise, if there's no regulation, there would be no need for us to be here and making safe systems. So, simplifying that approach, this is the task here at HMS, what we are doing. And I want to introduce you a bit to how we see the world from the standard factory automation. And what I could see of the last years is that the standard factory automation networks, communication protocols, they are more and more used in these mobile machines. And why is that? And what positive effects this can bring, you will see today. Well, first of all, how do we separate the systems? You are all involved somehow in AGV manufacturing or working with AGVs. So my view here is mobile devices, they are safe islands on wheels. As we've heard also before, we have the AGVs that may not have so much safety on board in terms of sensors or logic, but the AMRs they do have. Because we had the discussion about taking decisions, but still being safe on the decision what was taken on the road. You need safety sensors for that. This is typically inside the AMRs, into the mobile robots. So, safety sensors and logic already on board. And the local safe control is also on board in, I would say, 99% of the cases today. It's a homogeneous network. You have laser scanner on board, safety drives, safety logic that can quickly react on anything, any obstacle that goes into the way. And it's homogeneous network inside the vehicle. You need fast, safe reaction. We had the example before. If you step right in front of a moving vehicle, it has to be very quick in reaction, maybe less than 10 milliseconds to stop in time, that it doesn't crash into you. And as the regulation already says today, you need to have an emergency stop button at the edge of each mobile device. You must be able to stop it from any position. Sometimes difficult if you have high load on it to find a good place to place your emergency stop button. And here comes maybe also the stop button at the wall into account. It's important that you can stop some dangerous situation also from the outside, because the mandatory e-stop on board cannot be enough in some cases. But it is there. It's discrete local safety inputs, emergency stop in most of the cases. And when we talk about safety networks on board, we have today the laser scanners, and for the AMRs, it's essential that the laser scanners, they adopt their field of detection depending on speed or depending on the angle they are steering to. But this is all inside vehicle safety network. The logic inside decides what to do. And you typically, from the outside, if you want to bring an e-stop, as we've heard with the supervisory function, if you want to bring this e-stop into the device, there is no natural interface, because it's a closed network and there's no third-party access to it. Well, why is that important? We have, in the other corner, we have the industry, the fixed machineries. And here the situation looks a little bit different. Factory floor safety systems, they are often selected by end users or by the system integrators. It's not selected by the AGV manufacturer. That might have a very fancy safety network already inside, but you can't go to the outside with this network. So it's a separate network outside, different technologies. And we find often inhomogeneous safety network architectures. In the industry, we have maybe a factory floor controller, and we have a lot of cells independently acting, like robot cells. They have their own safety networks inside, but they are integrated in hierarchical structures, hierarchical safety structures. And here we come into the trouble because it's different safety networks. Robot manufacturer A has a different safety network than manufacturer B. So it's an inhomogeneous approach here. And we have the infrastructure to machine safety communication necessary. Yeah. In the distributed safety devices we see on the factory floor, we have the typical factory automation protocols. On the mobile machines, we sometimes find also proprietary solutions, but when it comes to interoperation on the machine level, we have the factory automation protocols that are standardized. Today, we probably hear about more about ProfiSafe, SIP safety, FSV. You might all already know these protocols. They are very famous in factory automation and also more and more in the mobile machines. So the challenge here is having this inhomogeneous outside safety network signals to bring them into the mobile device. We've heard about the supervisory function. It's important to stop a mobile device. Or we've heard about logging of events. If you press the e-stop button, someone has to log it. You can do it on the machine, but you can also do it on the mobile machine. You can also do it outside in some control center on the factory floor. Yeah, that's a challenge, attaching the mobile robot fleet. It's normally not only one robot you have to attach, it's several of them, to the processing on the factory floor. So we see this big gap in between, and naturally a mobile device, it doesn't have a cable, so everything has to go wireless. Means also the safety signals have to go wireless. And here the bridge has to be, or the gap has to be bridged between safety systems. Inhomogeneous, it's not wired. All the functional safety protocols like ProfiSafe, SIP-Safe, FSV, they are designed for wired first of all. But there is an approach to have safety signals over the air, and that's the black channel approach. We have the possibility also later on to talk more about what black channel approach is, but yeah, it gives you a possibility to use a wireless network even though it has reduced communication stability, to still be safe. And air, it's also a shared media. The more participants you have, the more communicate on the air, the more congestions you may have, the more delays you have. Delay and non-deterministic behavior, this is a killer for safety. Therefore, you need protocols on top, communication capabilities to detect any of these problems of the wireless network. And today we have several speeches about how to make safety over wireless. The approach that we are taking as HMS is using a standard IT infrastructure and standard Ethernet. It is possible, it's working, and with the right protocols, it does not even harm the safety of the signals. Another topic, roaming. You might know mobile devices traveling around. You don't always have a good signal quality, so you have several access points. You will start roaming between these access points, and roaming by nature brings more delays in the system. These delays for standard Wi-Fi networks, we have done measurements. They are in the range of 100 milliseconds. With specific algorithms and methods we hear also from R3 later on, you can drastically reduce the delays. But for standard Ethernet, 100 millisecond delay is already quite good. And wireless typically uses IT infrastructure. As a system integrator, you know that trouble. You're sometimes not allowed as automation person to bring your own Wi-Fi network. It's the IT department to deploy the network and to select the right components in the field. So it's typically IT infrastructure with all the pros and cons. How to solve the problem? I already briefly touched it. We have these protocols like SIP Safety, ProfiSafe that can be used to transfer safety signals over wireless networks. They are treating the wireless as a black channel. That means We have mechanisms like CRCs, so additional data which is transferred, cyclic redundancy checks, or timing measurements, addressing, that make sure that we detect any kind of failure in the system. That doesn't mean it's 100% stable with the black channel approach. It just means the safety signal is detected whether it's still safe or not on the receiving side. That's the basic approach. And stability of the network, availability of the network, that's a different topic. First of all, the black channel just makes sure that the signals are safely transferred from A to B. We have the standardized safety protocols here, like SIP-Safety or ProfiSafe. They're very good to be used on wireless networks, especially SIP-Safety. It's based on IP protocols, and IP protocols by nature can be very good routed through IT networks. ProfiSafe, it's a bit special, but also here there are possibilities. What needs to be done, though, is the standardized safety protocols, they're designed for wired networks. It needs to be adapted in terms of the network parameters. You have to increase timeouts, for example, or allow repetitions of frames that you can also deal with lost frames in the network. These are all adaptations you can do with the safety protocols to make them use on the wireless network still, and also increase a bit the availability of the safety signal. We don't want to have this nuisance trips or having stop of an AGV because it travels behind just behind some steel wall and you have no connection for a pretty short time. Therefore, you can change the network parameters to adapt to the wireless network quality. So finally, we can say the network quality, it affects, first of all, the maximum number of devices. We've heard about the shared media air, and the more are communicating over the air and the more repetitions you have on standard Wi-Fi, the less bandwidth is left for all the participants in the network. So one way of doing or getting more bandwidth, more availability, is reducing the number of devices if you have bad network quality. On the other hand, network quality affects also the minimum safe reaction time. Why is that? Well, if we start adapting the timeout time on the network, so the time where we allow no communication, this automatically increases our safe reaction time. Yeah, but the good thing is, network quality, it does not affect the safety integrity of the signal. Still, we can detect whether the signal was good or falsified on the way between sender and receiver. Well, to simplify the approach, that was also the name of the presentation today, simplifying the integration of SIP-Safety signals on mobile machines. We from HMS decided to make a compact box to bring safe communication and safe I/O into one box solution that is easy to use and standardized. So this new product can also show it on the table behind in the break. We have the Safe2Link Remote I/O, which combines this SIP-Safety over Ethernet IP, one of these standard safety networks. Next version is ProfiSafe over Profinet, bringing standard and safe communication on one wire. We are reusing existing wireless networks, no need for specific networks. Even so, you have to thoroughly think what is the quality of your IT Wi-Fi network in the whole factory floor. We can also use Bluetooth, for example, or 5G. We also made some trials from HMS side with 5G, which also has very promising results here. So that's one way of integrating safety using existing wireless infrastructure. It's type approved, ready to use, no additional safety certification. And the good thing for all these safety protocols, ProfiSafe, FSOE, or SIP-Safety, it's individually addressable. And we have heard this example from Dave before. When there's a mobile robot having trouble somewhere on the factory floor, there's the supervisory function, Someone has to stop maybe the whole factory floor, but what if you can stop only the devices around the device that needs maintenance? Therefore, you need individual addressing of safety. And this already comes by nature of the safety protocols. They are individually addressing each participant in the network. That gives much more flexibility also in the future. We show also the example here, when you go to a certain machine, you become part of a machine as a mobile robot. You're delivering goods to a mobile machine. You become part of this machine, and machinery regulation says that combined machines have to be in a safe stop. So if one part of the machine stops, all parts of the combined machine must stop. And this needs individual addressing. This comes by nature with ProfiSafe, SIP-Safety, FSOE. Another advantage for these protocols. With Safe-to-Link, no change in safety network is necessary. We have safe inputs, safe outputs, so you can loop through safety signals. And this covers also the problem that on standard AGV platforms, you don't have access to the safety network typically. Here, we are looping through, we have some safety functions inside that combine the outside safe signal coming over wireless with the inside coming from some sensors that are already on board. So safety signal as loop through and easy to add external safe stop into a mobile device using standard infrastructure on the Wi-Fi side and also using standard mobile vehicles. To bring this into a more technical scheme and to see also the different levels of safe and non-safe inside the mobile machines, just put it here as this in this matrix. If on the upper side, there's the outside factory floor network, where you typically have the warehouse management or factory automation PLC. On the left side, it's all the non-safe stuff. You also see the Wi-Fi router. It's also part of the non-safe side. On the right side, it's the safe side. We have the safe access control. Think about AGVs fenced off in some warehouse area, some confined zone. When you open the door to that confined zone, you have to stop all the vehicles that are behind because there's someone entering the infrastructure, placing additional risk to the machine that was not present before. So you have to stop here. And now we have to transfer this signal all the way from the upper right to the lower right side, which is the inside vehicle here, where we have also non-safe, the vehicle motion control, all the navigation, and maybe that's also part of discussion with Dave, what part of navigation is safe and what not. So navigation typically takes a decision to go left or right. But from the discussion we had before, if you're close to a confined zone, you're not allowed to go right. Then this is a safety critical decision. So you have to stay in, and normally the vehicle control, the motion control is doing that and not the safety system. On the other hand, we have the safety system, the safety sensors that check also for the speed of the mobile device. If you have an AMR that has adaptable fields on the LiDAR, you need to have the feedback from the motion to switch the different scanner zones. That can be a safety logic on board doing that. So it's all inside safety signals we process here. And now we can loop in the Safe-to-Link. So the decision of the safety logic to stop or to slow down can be looped through Safe-to-Link. And at the same time, Safe-to-Link has the outside connectivity to the safety field bus network that comes over wireless. And again, we see here, inside the vehicle, fast stop of motion is necessary. Within several milliseconds, you have to stop the local motion if someone steps into the way. If you enter the factory floor with the safe access control, you're typically further away from the mobile machines. Means you have more time to react. And therefore, wireless networks with hundreds of milliseconds of delay is normally not a big deal. You can still open the door and you're further away from the machine to have time to stop. But Our device here combines the slow remote stop together with the local fast stop. That's how we bring here the different quadrants together and combine it to a safe solution in the end. Yeah, we can skip that one just for completion. Yeah, so summing up, first of all, standardized safety protocol. We are supporting Ethernet IP SIP safety. It's conformance approved, which is also important when it comes to interoperation. Using a standardized protocol increases the probability that all the devices using this protocol are perfectly working together. It's conformance tested, also safe communication is conformance tested and is ready to use. For the integration, on the safe side, for the system integrator, Sistema library is available that simplifies integration. So safety figures are all given for the device. And for the configuration of the PLC, of the safety network, we provide the EDS file that gives all the features, all the functions, all the parameters of this device to the system integrator, to the one that is programming the PLC in the end. The safety field bus, it controls, first of all, we have this unique mobile device addressing I mentioned before, which is a nice feature for future position-based or function-based safety. Other than this, the safety field bus controls the safe outputs. That's the remote safe stop we talked about. And also the safe inputs are reported to this PLC via the safety field bus. That can be used for logging purposes, but it can also be used when we are talking about combined machine, that you can use the emergency stop of the mobile device directly on the stationary device if you combine these two machines. And this is all possible using safety field bus with the safe input from the device on board. Reducing recertification effort. You can think about integrating functional safety in your own control software. Then it's programming work on your side if you're designing a mobile machine. Or you can reduce that effort by parameterizing instead of programming. How is that? Well, this safety device, the safety link, provides configurable safe IOs. There are safety parameters which are transferred at startup. So you can adapt also to different situations in terms of remote configuration from the PLC side. We can configure I/O filters. You can directly connect OSSD sensor or an emergency stop button, contact button. That's all configurable. You don't have to program. It's just a parameter that needs to be set. Also sensor supervision. Emergency stop buttons for PLD, you have to check whether cabling is still okay. This is done with sensor supervision. Then another software function that is also helpful for mobile devices, especially if they are moving faster or carry bigger loads. That's a safe stop category 1. If you hit the emergency stop button, you don't want the AGV to immediately stop. It must have the time to ramp down. So we have also this safe stop category 1 on board to ramp down before safe stop. And the delay time here, it's configurable via safety field bus. Even at runtime, you can decide, depending on the load you put on the device, you can change the ramp down supervision or the ramp down time here. And finally, the safe bound feature, where we combine the local safe input with the remote safe input together on one safe stop signal, which brings fast local reaction and slow remote stop signal together. So in a nutshell, very quick, 4 simplified steps. First step is looping in an additional safe stop source. Could be either by a safe torque of input, which is provided by the robot manufacturer, the mobile robot manufacturer, or if this is not present, you can also hook up the emergency stop button to our device and just loop it through to the safety logic, which is already on board. Then the communication link, since we're using standard factory Ethernet, standard Wi-Fi, you have to hook up this safety link to the existing Wi-Fi network. And then comes the most troublesome work, I would say. Before it was just cabling and modification of the device. Now we come to the configuration part. You have to add the mobile safety device in the network configuration of the stationary side of the factory automation PLC. It becomes part of the stationary machine because you have to share the safe inputs, which are in the infrastructure, which are at the machine. You have to share them with the mobile device. And here you set up the safety relations, but also the safety parameters of the network. That's what we talked before, adapting depending on the network quality. You can adapt the timeouts of your safety field bus network. And finally, verifying the safe operation. For sure, you can do a lot of things in theory, but finally, practically it has to work. You have to verify all these features. And the configuration of the safety network is also part of the system certification in the end. It has vital safety parameters inside, which are specific for the machine, specific for the setup. So certification is also linking or fixing the configuration here. Yeah, that are 4 simple steps using the Safe to Link. We can have deeper discussions later on in the break. I can talk more about the product. And now I'm open for your questions.
Thank you, Stefan. Questions? There's Eddie from Gideon. I'm making the presentation. Thank you. Applause to Stefan and to Eddie, please.
First of all, thank you for the presentation. Wireless safety is definitely an important topic for us. And in the last year, we have been testing various solutions. And obviously, we tried testing kind of the standard approach of using the standard Wi-Fi. And to be honest, the results were pretty bad. We were not able to get the timings and the reliability of the communication. So my question is, what are you doing differently in that device that allows this reliability that maybe a standard without this device we cannot achieve? And are you doing any kind of protocol compacting or tampering to allow the reliability of the communication?
No, in terms of reliability, this product is not really improving things. It's still a standardized SIP safety device. And with all the troubles that you're mentioning, if you have bad network quality, we can't make it better because we don't touch the wireless interface. We just transfer the signals using this protocol to detect failures. You will have the trips still, but they are safely detected with the protocol. But we do not improve the Wi-Fi capabilities. No. I think we have other presentations today where you hear about what can be done to improve the wireless network. We were concentrating on using it for applications where the network is stable enough. So we have small range networks, but also 5G networks, for example, which are very promising in factory floors and give high probabilities and high availability of the network, independent from the network protocol.
Okay, so what are kind of the timings you can achieve with like the typical wireless clients that you use to test your solution in terms of like watchdog timeouts for the protocol that you can confirm will work reliably in some network configuration? What are we talking about here?
Yeah, I can just give some examples from what customers of us were doing. So for sure, in laboratory test environments, we came down to 150 milliseconds. That was possible also with some roaming tweaks. But typical applications that we have seen also in the field and our customers were telling us were in the range of 300 milliseconds cycle time on the Wi-Fi network. That was still good enough for them because the fences were very far away from the mobile devices. But 300 milliseconds and above, this is a typical value where customers can work with.